Good morning, everyone. Welcome to. Yeah, sure.
Watch the video. Jerome.
It's good. Okay, so I'm gonna talk to you about, as we said, different things. It's still early technologies, but it's things that we are developing at the Nanotechnology Institute in Bar-Ilan University here in Israel. I'm also ophthalmologist. I'm working in Jerusalem doing refractive surgery, and I'm in charge also of the research and innovation unit of the department. So here, the first slide, I want to acknowledge my colleague. That is a great team. I'm doing a couple of projects with them. You're going to see them throughout the presentation. Okay, so the question is, nanotechnology is started to be very popular for the past years in the medicine in general, and how something that small can be so big and has such an influence in our field. So let's just have some insight about nanotechnology and optics, and how we can get both together to kind of develop some technology for us. That is the type of thing that is already being done in the Nano Institute of Berkeley in the United States. They already developed an invisible cloak. They are using this in the US Army. They put that on the tank, and then if it doesn't move and there is no wind and so on, you can see through the tank. So it's pretty advanced thing they are doing there. But in terms of what we are doing every day in terms of optics, we're a little bit far from that. One of the most common things we have for correcting vision is glasses, right? And you can see that there is also some undesirable effect with glasses. So there might have some technological gap here that we have to find out a way to fill that gap. So that's the Institute of Nanotech in Bar-Ilan University. And that the first project I'm gonna talk to you about is nano drops, is eye drops to correct the refractive error. We are doing that together with a very heterogeneous team, because it's Professor Zalewski that has already more than 100 patents, 12 startups. He's a very successful guy in this field. He's leading the bioengineering department, which is exactly the building you are seeing here, and Professor Lelouch, who is the head of the chemistry department, and he's specialized in nanoparticle fabrication. So we came up with this idea of designing drops for correcting refractive error. We patented this technology a couple of months ago, and it's a funny story. I was already working with Professor Zalewski. I'm working with him already 5 years.
Patent is it in Israel or
in the United States? It's the patent office of the United States, yeah. But it's an Israeli patent, but you submit that there. And so I was working with him. I'm a researcher associate in this institute for the past 5 years. And the funny thing is, I was in France working there for one day, and I saw, I don't remember, like 50 patients a day. And everything was on computers, so I was the whole day on computer. And at the end of the day, I was feeling that for sure, if I was looking at my refraction, I would find a little plus half diopter or something like this. And because of that, I felt my headache the whole day. So I asked the optometrist to look at my eyes, and he found this plus half diopter. And you don't have much to do with that. It's all glasses that I didn't want. Refractive surgery is too small number, so because my eyes were tiring also, I wanted to have eye drops to get both the feeling of having something nice to lubricate my eyes and also to correct my vision. So the whole flight back I was thinking about that, and then I called Zev and I asked him, look, we have to sit and find a way to develop eye drops for correcting vision, because usually it goes together. So we looked for a chemist, someone that was like specialized in this field, and we found Professor Lelouch in the same university that was also specialized in nanoparticle fabrication. We said the three of us, and we came up with this idea that I'm going to describe you now. So that's for the story how everything started. I have to mention that everything started with no funds at all. And that's also another project that I'm going to show you that started this way. And this is one of the particularities that I like here. I used to work in France. It was kind of tough to make things happen in terms of research. And I found a way here to make things much smoother in terms of transferring the technology from a lab to a company. Okay, so that's the invention concept. The idea is to correct refractive error from home through a local corneal refractive index change. So it's a 3-step procedure that we are doing. The first step is something that already exists. We didn't develop this step. Probably some of you have heard about this. I'm sure in the future we're going to hear much more about that. The idea is to get your refraction and get your correction. As you can see here, the company called iNetra, but you have many other new applications available for that. And you can see, just put your smartphone in a small box, look at the small box, and after a few seconds you get your refraction. Don't need to go to the optometrist, to the ophthalmologist. You can do that at home, and it fits perfectly the rest of the technology you're going to see now. So there are pretty much 6 startups that have developed this type of technology today. Once you get your refraction, you are still at home, you get your refraction, and then you want to connect a very small laser device that you're going to clip to the camera of your smartphone. Sure.
Thank you.
So you want to connect a small laser device to the camera of your smartphone in order to print out onto the epithelium, onto the cornea, an optical design. I'm going to show you and you're going to understand better. So that's the step number 2, is the creation of a pattern onto the cornea. Okay, so you have here the smartphone. You put your correction into your smartphone in another application. You have, let's say you have a myopia -2. You have to look at the targets, and then in less than 1 second you just press a button and you get onto the cornea a specific pattern that will be printed out. Where he will be printed out? Exactly on the first 1 or 2 layer of the epithelium. The idea is to open the door for the nanoparticles that we're going to put onto the eyes to get into the cornea and activate this pattern. So we are talking here not to get through the Bowman, but working just onto the epithelium. So the second step is laser corneal superficial etching of an optical pattern. It's important to understand that we are not talking about ablation at all. We are just talking about doing a small etching, because usually laser is associated with the corneal ablation procedure, which is not the case here. So what do we mean by this, this optical pattern? Here you can see a couple of optical patterns we did in the lab on pig eyes. And according to the number you want to correct, if it's -2, if it's a little bit of cylinder, if it's presbyopia, we try different type of pattern that can work very smoothly. For example, for myopic correction, we can use exactly the same type of technology that Fresnel plate zone that allow us to have a very, very accurate correction, because with Fresnel plate zone, you can play with the numbers as close as a quarter of diopters. So that's, for example, for myopia, you can use an extended depth of focus one that I'm sure everybody knows here. For presbyopia, as you can see here, and extended depth of focus was first designed and patented by Professor Zalewski. It's one of his patents. The one that you see in Symphony is the one that he's developed in his lab, so he is very experienced in this pattern.
Why you do just a circle of 1 millimeter? Why it's so little?
No, it's not 1 millimeter. It's just for showing. Sure. The parameter, actually, it's a good question, but the diameter of the pattern, if it's for myopia, presbyopia, or astigmatism, is different for every type of number. So here you can see the extended depth of focus through a optical bench. And as soon as you did that and you print out this onto the cornea, you want to get to the next steps, that is putting eye drops onto the eye. You can see here eye drop that we are putting onto the eyes of pig. You can see in vitro the nanoparticles that we are putting here, and you can see part of the preparation of the nano drops here on the video. So the eye drops, the idea and the function of the nanoparticles here is to activate the pattern. Now you have small dots into the cornea. If you don't do anything, those small dots will be filled up with tear film. And then you don't change the refractive index, nothing will happen. If you put nanoparticles inside, the nanoparticles have their own refractive index. If you put the nanoparticle inside, you will create a locally change in refractive index. So you can see here, you make the pattern, and then you fill the small etching you just did, you fill that with the nanoparticles, and by doing that, you will activate the pattern, you will be able to change the trajectory of light because locally you will have refractive index change. So it's here you can see with the semi-electronic microscope, the nanoparticles, you have on the small side a cornea without anything, and on the right side a cornea filled with the nanoparticles. It looked like a small grapes. You see it's encapsulated nanoparticles. It's more like a tiny balls of 60 to 80 nanometer, but we can play with the size as well. And here is, it's a funny story, this one, because that's the first study we did, and I used to say that it's a double-blind story, a double-blind experiment, which is very high in terms of science, double-blind. What happened here is that the pig that I treated was obviously blinded because he didn't know which treatment he received. But I also was sure that I was treating presbyopia here. So I asked the engineer to prepare the pattern for presbyopia. And there was some kind of misunderstanding between us. And he prepared me the myopic pattern that I didn't know. So once we did this, I put the nanoparticles, I treated the 5 eyes, and then I started to make the statistics and look for the numbers. And everything looks perfect because he told me we're going to treat between 2 and 2.5 of myopia. And I can see here that I treated -2.25, and look at the standard deviation, it's pretty close. So almost all the eye were perfectly treated. But then I put that on the graph, and I say, well, there is here an issue because the graph is going down. So it's like I'm treating myopia. So I talked to him and I said, look, that there is an issue here because it almost worked, but exactly in the opposite direction. And then he told me that it was the myopic pattern, so I was feeling a little bit better. So it's a pretty easy experiment we did. We just look at with a handheld autorefractometer, the same one, the Retinomax. Probably most of you know this machine, the same one that we are using for children, for example. I look at the refraction of the pig eyes, and then we did the pattern. I took also 5 measurements each time to make sure there is a low standard deviation for each measurement and it was not randomly measuring something. And then every 15 minutes I was looking at the refraction change. And obviously, because it's also an autorefractometer, it's an autokeratorefractometer, I got the keratometry to make sure the refraction change was not due to the keratometric change. So you can see here that there is absolutely no change in curvature. So that's when we decided to look for myopia. We did the same thing for presbyopia, and we got pretty much the same thing here. After 45 minutes, it got stabilized for 2 hours, and then because it was ex vivo, I stopped the experiments because I started to feel like exhausted of this every 15 minutes 5 measurement. So keratometry again didn't change, and in few words, so we are at the stage of finish the ex vivo experiment. We are starting in a few weeks the in vivo to answer the main question, I guess, that we're gonna ask me about how long it lasts into the eye and what the duration of the treatment. So that's exactly what we're gonna answer with the in vivo treatment. And we are finishing raising funds now. We are signing next week. So we are finishing to raise funds to move on with the technology. So that's my colleague, Professor Zalewski on the left, and then Professor Lelouch on the right. this is a nice article that came out for the 70 years of the State of Israel, for the 70 years birthday of the State of Israel, and they took this startup for representing one of the advances in scientific discovery. So we look forward to present the next result, hope next year. Next year we plan to start the first human trial in summer 2019. And the second technology that we are developing and we have patented also a couple of months ago, it's also related to presbyopia. The idea, same place exactly, almost the same people. I still work with Professor Zalewski for this, and Professor Kruger, that maybe some of you know from the Cleveland Clinic. I did my fellowship with Ron 7 years ago, and we're still working together to do a couple of research together. So the idea here was to find a way to develop a new type of intraocular lens using nanotechnology, and the idea came from that type of observation. You are sitting in a coffee, and this is a view through a smartphone. So let's say you have presbyopia. You are looking here at the street, and you can see perfectly the distance, but your cup of coffee is still blurry because you don't have accommodation. But the crazy thing is when you use your small device that everyone of us here have in the pockets, you can perfectly just put your iPhone on the cup of coffee, and then suddenly it came into focus, right? So the idea was pretty simple. The idea was to put an iPhone, like a smartphone, into the eyes and have the same type of technology. How come we cannot have such a thing today? So if we just come out from everything that I just said, and we are just looking at the technology we are using in our daily practice, it's much more advanced than one we are using every day. We have a smartphone with cameras, with different pictures. We can play with that many times. We have fantastic resolution. We have that in our iWatch today. We can look at the news. And we even have that today in our operation room, because today we have augmented reality for many of the applications for toric IOL, for example, here. So how come, sorry, you want me to go back there?
Very beautiful.
So how come, in terms of optics, probably the most popular things we can implant to our patient is still diffractive, apodized diffractive optics, with the basic idea that is working, but still we have to split the lights, lose energy, decrease contrast sensitivity, and then you have this very well-known effect of night vision symptoms, because you have the light of one focus going to the retina out of focus, and people are still complaining about halos and glare. So this does not perfectly match with the everyday technology we have today. And the idea here of the smart lens we developed is to use, I'm doing that microscopic for us to understand, but obviously this multi-element lens, as you will see in a moment, will fit in both for a pair of glasses, because the patent is on a lens. So the lens can fit for glasses, but can also fit for intraocular lens. So the idea is to use, again, nanotechnology and nanoparticles to make this technology efficient. So imagine you have a multi-element lens. You have a couple of lenses that you're going to see here. The light is coming from outside, striking the retina. Now you want to put on a lens that you have into your eyes, coating surface made from semiconductor nanoparticles with what we call tunable reflectivity. What does it mean exactly? You have a coating surface onto your lens. Imagine you have a lens. You have in both sides of the lens, as you saw here in pink and in orange, in both sides of the surface, in both surfaces of the lens, you have a coating surface made of nanoparticles. Those nanoparticles react with a specific wavelength from outside. When you absorb with those cutting surface, when you can absorb the photon from the light, you will create an excitement of the nanoparticles. You will make them in an excited state, and as soon as you absorb those photons, the energy is coming up, and you are releasing what we call free carrier, which is basically electrons that are turning around exactly at the surface. But what is fantastic is when you have those free carrier and electron turning around, you modify the reflectivity, which means that we can play with the lights to make sure they will strike back and forth the different surface exactly the number of times we want to change the focal length at the end, as you can see here. So we externally control this reflectivity. We just have to press a button outside, and then you can see that you can just modify by doing way back and forth between those two surfaces. You can just extend and increase the optical focal length. But we can do another thing, is we can add another lens inside that will have another semiconducting surface with also nanoparticle, but will react with another wavelength to make sure not to get confused with the other one, in order to artificially extend the trajectory of light into the lens, which is not true. But if you are doing back and forth, the traveling of the light into the lens will be higher, even though it will just be back and forth. But in terms of distance, the light will travel inside the lens, it will be higher. And why we are doing that? Because when you increase the distance of the light, of the travel of the light into a surface, you can create a zooming effect. So by doing that, we can create a zoom, and we can achieve a zoom by a factor of 3 without having any moving part into the lens that we know today is an issue.
So on the other side, you will be very far away.
You can. So that
not only from here.
Yeah, exactly. So the idea to do that, it was for people with AMD that have to magnify the picture to be able to see. This is what we obtained. So that's a basic formula that we can use to decide the number of focus we want to have. This is the schema you have, and this is a basic experiment we did in optical labs. Professor Zalewski, you can see here through the TV, you can see on the small side a chart that was located at 80 centimeter. And we activated the focus to make sure we'll be able to see 80 centimeter. And on the other side, we put another chart at 30 centimeter, and we have to activate the 30 centimeter. We activate the number of back and forth that the light will do between those two surfaces, like this, to make sure the light will be getting at 30 centimeter. And you can see, I'm sorry for the flash here, but you can see on the right part now that we are able to see the 30 centimeter chart that was located there.
How do you activated this two layer, these nanoparticles? You have to
from outside.
From outside.
The basic application will be, for example, if you have on your smartphone the wavelengths we decide for activating the focus, and you know every time your lens will be in eye contact with this wavelength, that usually will be in infrared, that is the safe one. Every time you will look at your smartphone, when your smartphone is turning on, then you will activate your lens to be able to see. It takes like milliseconds to reorganize the lens, and it takes milliseconds to go back to the first initial distribution. So when you are in contact with your smartphone, you are in focus. When you are in contact outside, you are already in focus for distance. So when you are distance, you have 100% of the energy that is dedicated for distance. There is no compromise. There is no 40% or 50% of the energy.
It's infrared. It's not a Bluetooth or another wavelength.
No. It can be many. We can play with many of those that are triggering the lens. Obviously, you want to make sure we have a special filter to make sure that the ambient light won't activate anything. Obviously. And this is same thing. This is when you activate the other part of the lens, and you can see here that we can bring, just again, sorry for this poor quality, you can bring the charts up and increase the picture by a factor 3 that you have here, and you have the optical, again, the optical formula to create a zooming effect in such a situation. Now, if you want to see even beyond, if I'm asking you who today would buy a mobile phone that is just limited to call, I see you all right now taking pictures with your smartphone, right? But it was supposed to be able just to give you the possibility to talk. But here you are using that as a camera. So who today would take this phone? No one, right?
No, anti-collector.
Everyone is willing to get this smartphone. So my question is, how come you want to implant a lens into human body, just limited to see better? If we are already putting something inside the body, why would you limit yourself to correcting vision?
I will take some movie for tonight.
So
ask your wife, she will change the lens.
That does more than just fill you up.
yeah, that's true. That's right. So the second part of the technology, this is already patented technology. It's another startup that is not mine. It's the startup of Professor Zalewski. But the first time I met him to talk about implanting a smartphone technology into the eye, he told me, well, we can do that, and then I would love to add another technology that I just patented. It was 5 years ago. Today they just raised the third round of investment and just got 20 million for these startups. It's called Continue Use. It's a very successful thing, and they are able, just with a laser, exactly as we will activate the lens for changing the focus and making the zoom, with the same type of laser you will be able to get your blood concentration, you will be able to look for your intraocular pressure, look for the oxygen you have in the blood, the pulses, the heart pulse you have, and so on. So it's a fantastic technology. And just to give you some numbers, but among the whole US population above 65 years old, which is the target for cataract surgery, you can see that you have one third of people that have comorbidity, if it's diabetes or if it's glaucoma. So the technology that we want to connect to this lens are for glucose monitoring, IOP monitoring, and obviously AMD monitoring as well, the three big comorbidity we have. Well, thank you very much for attention.